what I have here is sort of the summation of these three sinusoids right here. All right, so I sum up these three sinusoids, and the waveform looks like this. And I call it the time domain because my x-axis here is time. All right, now looking at these three sine waves right here, which one's the highest frequency and which one's the lowest frequency? Which one? Yeah, this is the highest frequency. This is the lowest frequency. And basically the idea here is when I'm in the time domain, what I do is this is the real world, right? If I have a microphone that measures an audio signal, then that microphone picks up this time domain waveform. Through processing, I can basically convert it over to what I call the frequency domain and basically say, well, it has some information at this low frequency, some information at this middle frequency, and some information at this higher frequency. And I'm using this term information kind of loosely because I know what it's saying is somehow whatever's contained in here is information, right? Somehow I've put something into this signal that means something, right? Could be from my voice or whatever, right? Or it could be, like I was saying, if I tried to press the one key on the phone, there's two signals at two different frequencies. So two sine waves at two different frequencies that are getting added together. And somehow I'm doing the processing to figure out which ones are there. All right. So we have this idea of what we call the time domain versus the frequency domain. All right. Now to understand this thing, I want to kind of to try to say, if I think about sort of a pure cosine waveform, right? In the time domain, what I have is something that looks like this. Right, so in this example, I'm saying I've got x of t is 3 cosine 2 pi t minus 30 degrees. All right, so look at that thing here. What's the frequency here that we have? What's the frequency in radians per second for this particular waveform? 2 pi. So what's the frequency in hertz? 1 hertz. Not one hertz. 1 hertz. All right. So if I said, well, in the frequency domain, where would you expect there to be information? What location would you expect there to be information? What's that? 0? 0 in the... Yeah. Yeah, so I would expect there to be something at 1 hertz, right? On the spectrum analyzer, there should be something at 1 hertz. And that would be on the right side, I guess. Well, so I understand. On my screen, it would be on the left side of that. Yeah. At 1 hertz, right, is where I would expect there to be some information. Okay. Question is, how do I relate it to this? What's the processing that kind of happens behind the scenes? All right. Before I go too far down that line, one of the things that I want to remember is how would I want to express this in the different forms of the series for a second. All right. So x of t in this case, let's say I want to put it in this form. The n equal minus infinity to positive infinity, alpha n e to the j n omega naught t. I want to put x of t in that form. Now, first of all, what this says is x can have an infinite number of harmonics, but it doesn't have to. In this case, it only has how many? In this form of the series, how many harmonics does 3 cosine 2 pi t minus 30 degrees have? 2. In this form of the series, we say there's one at what 2 frequencies? N equal 1. Where's the other one? N equal minus 1. All right. If I did one of the other forms of the series, then yeah, it would only be at n equal 1. All right. Now, why n equal 1? Well, because I only have one term, so there's only a fundamental here, right? There's nothing else to worry about. So what would this guy be in that particular form, in the complex form? How would I write this out for this particular waveform? Okay, yeah, so there's a set of formulas I've got here, and I can go to those formulas, right? But I should be able to look at that thing and go, I got a single cosine, so I can use Euler's identity, right? So what's that tell me here? So it would be 3 over 2 times what? E to the what? All right. Let's do it. 3 cosine. Let's do this. 3 cosine theta, where theta equals 2 pi t minus 30 degrees, right? So I can write this as 3 e to the j theta plus 3 halves e to the minus j theta, right? Then I can substitute in this thing right here. And that's going to become 3 halves e to the minus j 30 degrees e to the j 2 pi t plus 3 halves e to the j 30 degrees e to the negative j 2 pi t. All right. Yeah. Do I have an n equals 0 term here? That's not 0? No. Yeah, I mean, technically I could go from n equal negative infinity to positive infinity, make them all 0 if I wanted to, right? So in this case, which one of these is alpha 1 and which one is alpha minus? There's 2 coefficients here, right? Which one's alpha 1 and which one's alpha minus 1? This is alpha 1. This guy is alpha minus 1, like that. All right, so I've got the 2 coefficients here that are there. Now, the idea of the Fourier transform basically is this. It tells us the frequencies where our signal has energy, okay? Now, there is a whole definition for a Fourier transform. Fourier transform applies to periodic and non-periodic waveforms. Fourier series only applies to periodic waveforms. In this class, I'm only going to focus on the periodic signal. What it says here is this. We use the impulse function to define a Fourier transform. And we basically use this formula right here. And basically what happens, bless you, we have impulses at the specific frequencies where there's information in the signal, okay? So this is the sort of the approach that we take, all right? A couple of steps to it. It's not that complicated. We actually know how to do the first couple of these, all right? So basically, if I have a periodic waveform x of t, and it has a Fourier series in that form, which it does. If it's periodic, it has a Fourier series in that form. Then it has a Fourier transform, or sometimes we call a frequency spectrum, because it's related to that spectrum analyzer. What's it look like across a spectrum of frequencies, right? That is defined like so. So we got to figure out what that kind of means here. And to find the Fourier transform of this thing, there's basically 3 steps. We determine what the Fourier series coefficients are. What are these alpha n values? Then we figure out how to map those to appropriate frequencies. And then we determine this x of omega. That's the Fourier transform. We determine that as a sum of impulses located at the right frequencies. Okay. All right. So let's go back to this particular thing. Let's see if we can make sense of this. So what I have here is this guy. And you guys just told me that this guy becomes, as a Fourier series, 3 halves e to the negative j 30 degrees e to the j 2 pi t plus 3 halves e to the j 30 degrees e to the negative j 2 pi t. Like that. Okay. So at what frequencies is there sort of information here? What's that? 1 hertz, right? And so if I'm talking about it in omega, right? So what values of omega do I have information? 2 pi and negative 2 pi. All right. Do I have anything anywhere else? No, I don't. So here's how I'm going to do this. So we had said that this x of omega was expressed like this. Alpha n x of omega minus n omega naught. Okay. So how could I place something? So I want an impulse that would be located at 2 pi. How would I get an impulse that's located at 2 pi? So at omega equal to 2 pi, how would I get an impulse located at that particular point? How would I express that? Well, so this thing is a function of omega. Okay. So how would I do that? How would I get an impulse located at omega? Forget time. Let's just say I told you I wanted to have an impulse located at t equal to 2 pi. How would you do that? How would you express that? Minus 2 pi. Yeah. So basically, I want something like this, omega minus 2 pi. Because go back to my original idea. So when I'm looking at this, my x-axis is frequency when I'm talking about this Fourier transform. So there's no difference in what I did when I was in the time domain. All the same rules apply for shifting, right? This could have been x instead of omega or t, right? I'm talking about my x-axis variable. I'm just giving my x-axis variable a different name. All right, how would I get something located at negative 2 pi? That would be, yeah, omega plus 2 pi. All right. So the way I'm going to interpret this summation here is I have alpha minus 1 at delta of omega minus plus 2 pi plus alpha 1 at omega delta of omega minus 2 pi. So what I'm saying here is I have information here. This is my omega equal negative 2 pi. This is my omega equal to 2 pi. Right? Because what I'm doing is so by having a negative sign here, I'm shifting the impulse to the right. By having a plus sign, I shift it to the left. All right. So this is the way that I sort of try to sketch this thing. Basically, what this impulse says is I have information only at those two locations. There is no other information anywhere else. All right. That's sort of the basic idea. Now, if I asked you to make a graph of this thing, let's plug in. So alpha minus 1 and alpha 1, let's plug them in. So I have 3/2 e to the negative j 30 degrees. Sorry, this one's the plus. All right. Plus 3/2 e to the negative j 30 degrees. Like that. How would I draw a graph of that? They're impulses, right? So how should I draw them? Just put the impulses at those locations, right? Except that's kind of hard. Because what am I sketching at those locations? What's that? Well, there'd be impulses, but I got impulses multiplied by something, right? Impulses multiplied by complex numbers. That's a funny concept, right? What I have here, this x of omega, what it is, it's a complex function of a real variable. All right. In other words, x of omega is a complex number. What about frequency, though? So I'm saying this is a function. It's a function of a real variable. What about this omega value? Is that a complex number? Do I have complex frequencies? No. So what I'm saying is the argument here, the independent variable is omega. That's a real number. The output of this function is a complex number. All right. So that means if I wanted to visualize this, if I wanted to graph this, I have to make two graphs, right? One for the magnitude and one for the angle. They have to be completely separate. All right. Now, this idea of a complex function of a real variable is something that if you want more information on, it's described in section 4.6 in the book. So back in chapter 4, when we first started about complex numbers, we didn't talk about complex functions. All right. It's a pretty simple concept. It basically is to say that there's actually two things for me to graph. At each of these locations, I have to plot a magnitude and an angle, two separate graphs. Okay. So as an example, let's say I have this guy, right? I have 3/2 e to the negative j 30 degrees at delta of omega minus 2 pi. All right. So let's think about it like this. There is a magnitude and an angle. Let's think about the magnitude of that thing. What is the magnitude of that? 3/2. Where? At what frequency is it equal to 3/2? If I have delta omega minus 2 pi, at what value of omega is that equal to 3/2? Yeah, at omega equal to 2 pi. 0 otherwise. All right. How would I express that there if I tried to show that magnitude versus frequency? Yeah. So I'd have this delta function, which I would scale by 3/2, and I would say that this is located at 2 pi. All right. Now I can also say I have an angle of h of omega. How would I express that? What's the angle of that thing as a function of frequency? Well, it has only one value at one location, right? Yeah, it'd be negative 30 degrees at omega equal to 2 pi. And it'd be 0 otherwise. So how would I graph that? Yep. So what did I just do? Okay. Not sure what I did. All right. This guy is negative 30 at omega equal to 2 pi. So I have two graphs that I draw. Basically, two graphs to express one complex number. Now, you can also do, if you want to do the real part and the imaginary part, but that's typically not as useful to me as the magnitude and the angle for reasons that we'll see, right? But if you're designing something like a filter or something like that, which you guys had filters in the first project, you'll have filters in 2112 with Yahoo. You'll probably be drawing, I don't know, maybe have you done Bodhi plots yet? Starting it. Okay. Basically what the Bodhi plot is you have you get what's called a transfer function. Maybe he's used that term, right? That transfer function is a complex function of a real frequency. All right. And so you will end up drawing a magnitude plot and an angle plot versus frequency. And most likely he's only going to ask you to draw the magnitude plot. Right. He doesn't worry probably as much about the angle plot. All right. Now, this concept I need to apply in general. So if I have, all right, so graphing this thing, if I ask you to graph this, basically if x of omega it's got these sort of special features, right? So it's got two issues. It's a complex function of a real variable, which means you need to make two graphs, right? So I got to draw the real valued magnitude, right? So in other words, what I'm saying is if I look at the magnitude here, the magnitude is a real number. The angle is a real number. I can't plot a complex number, right? Versus a real input. So what I do is I make two graphs. One graph is the real valued magnitude versus a real valued frequency. And the other one is the real valued angle versus the real valued frequency. Now, the other issue in trying to graph this thing is it consists of impulses, which is kind of a weird thing to draw. So what I can do if I want to make that sketch, and it's the thing that I ultimately ask you guys to do, is you use something in MATLAB called the stem command. And the stem command basically draws for us a series of impulses. So in this case, all right, I give it this command right here, stem 1, 2, 3, comma 4, 5, 6. What that's going to do is at the x values 1, 2, 3, it's going to have impulses that are heights or areas 4, 5, 6. All right, now the heights are going to be that, but we know what's the true height of an impulse? Infinite, right? But the area is what we usually try to represent. So this guy, even though the heights will look like 4, 5, and 6, they're really areas that it's referring to, right? All right. So what we ended up with, we basically said was this. Now, what we got to do is we got to think for ourselves. All right, what would this graph look like? How would I graph in particular for this particular thing? So I got two graphs that I got to make. So we basically said there were 3 steps in our process. If I go back to the way I originally defined this, all right, 3 steps in my process. I determine the Fourier series coefficients, right? Then I map those to the right frequencies. And then I determine x of omega as the sum of impulses located at the right locations. So we've done all that. All right. All right. Basically, I've said, all right, for this particular waveform, x of t equal 3 cosine 2 pi t minus 30 degrees, I've got impulses, this one and this one. All right. So I want to sketch both of those two things. So I want to sketch for myself what would I can think of this thing as a magnitude and an angle. Like that. All right. So let's write out first x of omega. I want to think of it as sort of a piecewise function here. So where does x of omega have stuff going on? Where are their values, and what values do I have? What 2 frequencies will I have information here? 2 pi at omega equal to 2 pi at omega equal to negative 2 pi, and everywhere else it's 0. Okay, so what would that look like here? At omega 2 pi and omega equal negative 2 pi, I basically just take the magnitudes of those 2 coefficients. What are they? Yep, 3 halves and 3 halves. All right. If I say now, I also want to figure out the angle of x of omega, what's that going to look like? Yeah, so again, omega equal 2 pi, omega equal negative 2 pi, and then otherwise. All right, at omega equal to 2 pi, what's the angle? Negative 30. So which of the 2 impulses did it come from? This one, right? Because so if the shift to the right happens with the negative sign, right? So this guy would be 30 degrees, and it's 0 otherwise, right? So how would I sketch that? So if I have, make a set of axes for myself here. So if I have, so unlike what I had before, my frequency is labeled, my x-axis is labeled in terms of omega, in terms of frequencies. In this case, I've got it set up as radians per second. And I write the magnitude of x here, okay? And similarly, the angle of x of omega here. All right, now the only areas where there's anything going on is at 2 pi and negative 2 pi. So at negative 2 pi and 2 pi. So how do I represent that? So on the magnitude side, what do I say? I've got 2 impulses, right? Where are the 2 impulses? 2 pi and minus 2 pi. So I'd show one here. which has an area of 3/2, and I show one here, which has an area of 3/2, like that. Now, what do I do on the angle side? Well, one's positive and one's negative. The one that's negative is the one at 2 pi, and the one that's positive is the one at negative 2 pi. So I'm going to see this guy is negative 30 degrees. This guy is 30 degrees. This is negative 2 pi, and this is 2 pi. Right? So that's how I express this. So that's kind of similar to what I was trying to show when I had that graph on my phone, right? What it was only showing for me really there was the magnitudes. And the fact that it was higher at some frequencies than it was at others is because there was just more of an amplitude at those frequencies than there were at the other ones. Okay. So, all right, how would I go and graph that? Well, all right, so here's an example piece of code of how I would do this, right? So what did I do? So I created an omega vector, right? And I put locations at negative 2 pi and 2 pi. All right. And then I created my X. This is my Fourier transform here. So basically there's 2 entries here. So there's 2 entries in the X vector, right? Because I'm going to plot those 2 together. And this is the value I should have at negative 2 pi. And this is the value I have at 2 pi. Now notice what's true about every trig function, including exponential in MATLAB. What angles, what units does it expect? Radians. All right. So I put stuff here in radians. And then what I have here is where I call the stem function. All right. So, and I'm using, we talked about this a long time ago, the subplot command. Right. So what subplot does in this case is going to show 2 different graphs stacked on top of each other. All right. And I have, what's this abs x? What's that going to plot? The magnitude. And then angle of x is going to plot the angle, right? So if I run this here, all right, so I get this result. All right, so what do I see? I'm seeing that 2 pi, well, 2 pi should be right about here. It looks like this is 6, right? So 6.28 is where 2 pi should be, right? So I see values here at 1.5. That makes sense, 3/2. And then I see my angles. I see negative 30 and 30. Now, in the homework, you're going to have stuff where, and this is maybe where you were going with this, is, you know, I might ask you to say, all right, well, I also want you to include the fact that there could be a DC term. So if that was the case, I would put a 0 in the middle of that, right? To say at omega equal to 0, there's nothing, right? So if I replotted that, this is just going to draw a 0 right in the middle. All right, to say that nothing's going on right there. All right. Now, I don't have to do that, but I think in particular in the homework, it probably asks you to do it for every frequency between a certain, or every harmonic within a certain range. Yeah. All right, so it's a fairly straightforward sort of thing to do. Now, the question is when you get a more complicated one. So if you look at it, I think you in the homework, I give you something more like this one here. All right, where I give you this waveform, right? So in I think in problem 3, I give you something like this where you got to say, all right, that's a periodic waveform. So I got to go through the steps, right? What were the steps? The first step was to figure out what are the alpha n values. The second step is to map those alpha n values to the right frequencies. And the third step is to figure out how do I get them into this formula right here, this x of omega formula. All right, that's what you do in problem 3. Problem 4, what do I ask you to do? Problem 4, I ask you to do it for one of those more arbitrary looking periodic waveforms. I think I explicitly asked you to do it for problem 2. So for problem 2, you got some waveform that's like I don't know, it's a trapezoid, I guess. And you do it for that trapezoid. And you have the alpha n values from problem 2, so you got to take that and you got to sort of get it into this form. All right, so that's without, I don't want to overload your brains too much more. We got 5 more minutes left, but I'm going to stop it there. We're going to go through this example on Wednesday. All right, and walk through how I would go through those steps. How do I get this into a Fourier series? How do I get those coefficients to particular frequencies? And how do I write the x of omega? All right.